Hello class, we're going to look at some trig identities today. Now the first thing we need to do before we get started with the notes is adopt a certain mindset. Since we're starting a new unit, that means brand new material, we're going to be doing stuff that is not as straightforward as we've done in the past. Each problem is going to be very unique. Each problem is going to have multiple ways of solving it. Now this doesn't mean I can't give you the best advice possible for solving each of these problems, but there is more than one way usually to solve some of these problems. So you'll have to kind of be creative when you solve some of them, but you'll also have to look at each problem individually and not rely on problems that you've solved on the past. Doesn't mean you can't use them, but it's not, okay, I did this in the past, so I'm going to do this here. It might be totally different. Okay, so example 1 is actually a review problem from the past unit. Find sine and cosine if tangent equals 5 and sine is greater than 0. So this was when we set up a coordinate plane. And we know that tangent is positive. So tangent is positive in the first and the third quadrant. And sine is also positive. Sine is positive in the first and the second. Yeah, that's right. Second quadrant. So the quadrant we're going to be using is the first quadrant to set up this triangle. So I'm going to go ahead, set up a triangle in blue. Okay. Tangent is 5. That's 5 over 1. So that means my opposite side is 5. My adjacent side is 1. And we'll use Pythagorean theorem to solve for the hypotenuse. And we will get 1 squared is 1, 5 squared is 25. Add them together, you get 26. Okay. Square root. So C, our hypotenuse, is square root of 26. So sine, usually we're finding all remaining trig identities for this, but this just asks for sine and cosine. So sine is 5. Remember, it's opposite over hypotenuse. So that's 5 over root 26. Take the time to rationalize the denominator if you so choose. Cosine is adjacent over hypotenuse, so adjacent is 1 over root 26. All right, now here's where the identities come in. So you're going to want to have the identity sheet that was given to you out in front of you. And I will be referencing this throughout the video. So it gives us that cosine x equals 0.34. And we want to find sine of x minus pi over 2. So what you're going to want to do is look at the cofunction identities. And there's a cofunction identity that says sine of pi over 2 minus x is equal to cosine x. Okay? Now, this is going to be very handy to us. Now, it's not quite a one-to-one translation because we have x minus pi over 2 on the input of our sine function here. So remember that subtraction is not commutative. So x minus pi over 2 is not the same as pi over 2 minus x. But what we can know is that x minus pi over 2 is the same as negative pi over 2 minus x. So, and if you're ever thinking about, hey, I'm going to flip that around the minus sign, that's free. Feel free to go ahead and do that. You'll have to put parentheses around it and add a negative on the outside. So what I'm going to do is I'm going to take this sine of x minus pi over 2, and I'm going to change it to sine of negative pi over 2 minus x. And again, you can do this no matter what the input is. You can, a minus b in general will equal negative b minus a. And likewise, b minus a will equal negative a minus b. This is one of those tools that you can use to solve problems like these. Now, we have sine with a negative and then pi over 2 minus x. We want to do something with this negative. So the second thing we're going to look at is the negative angle identities. And there's a negative angle identity for sine. It says that if sine has a negative angle input, that will equal the same as a negative sine x. So sine negative x equals negative sine x. Now, if we think about the unit we just finished, this is effectively saying that for sine, a reflection across the y-axis is the same as a reflection across the x-axis. So we're going to go ahead and do that. It's kind of like we're factoring the negative sign out of it. Negative sine pi over 2 minus x. Okay, so now we've got something that looks like this. Sine of pi over 2 minus x is equal to cosine. Well, what was cosine equal to at the beginning of the problem? Cosine was equal to 0.34, so that means this is equal to negative 0.34. And that's the end of our problem. All right. Another problem involving simplification. So the goal with these types of problems is always to make sure we take this kind of extensive expression we have here. We have sine cubed x plus sine x times cosine squared x. And oftentimes these problems are designed that we're going to be able to whittle it down to just a single expression, whether it be sine or cosine or tangent. By the end, I'm looking for something that might look something like sine, cosine, tangent, secant, cosecant. Okay? So we got to think algebraically in these terms. What do I have in common? Well, across these two terms, I have sine cubed. That's just sine times sine times sine. Okay? And on this other one, I also have a sine. Oops, sorry, glitching out. There we go. So both these terms have a sine x in common. So I'm going to go ahead and factor one out. So I'm going to take sine x. And then what do I have left over? Well, if I factor out sine x from sine cubed, I have sine squared left over. And if I take sine x out of this term right here, I just have a cosine squared. So this is going to be very handy because it gives us one of the identities that you're going to come to love above all else. This is a Pythagorean identity. So go ahead to your sheet right now and look at the Pythagorean identities. And you'll see that it says sine squared x plus cosine squared x equals 1. So that's what I'm going to do. I'm going to substitute 1 in for sine squared x plus cosine squared x. And because we're multiplying, anything times 1 is itself. So my final answer is sine x. And you can check this answer. Oftentimes it's nice to check these graphically. So if you typed sine cubed x plus sine x times cosine squared x into Desmos, and then separately type sine x, you'd see they'd have overlapping graphs. All right, so another simplify the expression problem. Let's go ahead. I see I've got two factors, kind of like binomials. And anytime we got binomials, it's sometimes best to distribute or FOIL them out. So I'm going to FOIL secant times secant x is secant squared x. Okay, secant squared x. And then I got minus secant x. And then I've got plus secant x. And then 1 times negative 1 is minus 1. I'll go ahead and put sine squared x underneath. We haven't done anything with that yet. And if you didn't notice from the outset, this is just a difference of squares, the factored form. So secant x and negative secant x are going to cancel. So I'm just left with secant squared x minus 1 over sine squared x. Here's another instance. We're going to look at secant squared x minus 1. That's another Pythagorean identity. It's a variation on 1 plus tangent squared x equals secant squared x. With this being a Pythagorean identity, if I subtract 1 from both sides, I will get tangent squared x equals secant squared x minus 1. Okay, so that means I can substitute tangent squared in for secant squared x minus 1. Okay, now we're still not quite there yet. because we got tangent and sine. Oftentimes when you get to a point in a problem like this, it's nicer to turn everything into terms of sine and cosine. We could have done that at the beginning with secant, but it would make things look a little bit weirder, and this identity doesn't represent itself quite as nicely. So we're going to take tangent. If we look at our quotient identities, tangent is equal to sine x over cosine x. And because tangent is squared, this time it'll be sine squared x times cosine squared x. Over cosine squared x. Okay. Now what we have here is a complex fraction. So let's go ahead and simplify the denominator of the complex part. So I'm multiplying top and bottom by cosine squared. This will cancel out, and I'll just be left with sine squared x in the numerator, and I'll be left with sine squared x times cosine squared x in the denominator. And now we can simplify. We're just dealing with a fraction here, so these sine squareds can cancel out, and I'm left with 1 over cosine squared. And that would be a fine enough answer, but we can take it one step further. Cosine, or 1 over cosine squared. 1 over cosine is one of our reciprocal identities, so this would be secant squared x. And we're done. Okay, so now we're going to look at one more expression where we're dealing with fractions here. We're dealing with subtracting fractions. Now, this is not as bad as it looks. We have to think about what we know about fractions and what it means to subtract them. When we're subtracting fraction, we always need a common denominator. Now, it looks a little weird when we're dealing with trig expressions, but what we're effectively going to do, we got this 1 minus sine x here, and we've got the cosine x in the denominator over here. Well, finding a common denominator with algebraic expressions as opposed to numbers is just basically saying, okay, 1 minus sine x, what am I missing? I'm missing a cosine x. So I'm going to multiply this by cosine x. And what I do to the top, I must do to the bottom. Okay. And over here, I've got a cosine x. What am I missing? I'm missing a 1 minus cosine x. If this isn't clicking yet, I'll explain it to you this way. When we've got fractions, say I want to add 2/3 and 3/4, I need to look for a common denominator. Well, we think about and see that 3 and 4 have a common multiple of 12. That means I multiply here 4 and here 4, and over here I'm multiplying by 3 and 3. It's the same idea. I have a 3 here. I'm missing the factor of 4. And over here I've got the factor of 4, and I'm missing the factor of 3. So we've got to reintroduce what it's missing. So let's simplify. Cosine x times cosine x, that's cosine squared x. And I'll actually even begin to write this as one fraction now because I have a common denominator. Now, one thing I'm going to do, actually, sorry, I just noticed a mistake. It should be 1 minus sine x. Apologize for that. One minus sine x. Apologies, there we go. And what I'll do is I'll go ahead and distribute this. So I got sine x, so I got minus sine x. Now be careful, I'm distributing technically both the negative and the sine x. So negative sine x times the negative sine x is plus sine squared x. Now, this is something you learn with experience, and you get the benefit of my experience. I am not going to distribute this cosine into the 1 minus sine x in the denominator. And you'll see why here in a second. So I got cosine x times 1 minus sine x. Now we have a cosine squared and we have a sine squared. What more, this sine squared is positive and this cosine squared is positive. So we can rearrange the terms in the numerator to make it a little nicer to look at. Cosine squared x plus sine squared x minus sine x all over cosine x times 1 minus sine x. And we've got our Pythagorean identity again. Usually Pythagorean identity is written as sine squared x plus cosine squared x, but addition is commutative, so it's the same forwards as backwards. We've got 1 here. Just remember to take the cosine squared sine squared part out. We got 1 minus sine x all over cosine x times 1 minus sine x. Now, this is why I did not distribute the cosine x to begin with, is because now I can see I have a factor of 1 minus sine x in the numerator. I have a factor of 1 minus sine x in the denominator. I can cancel those out. Now, anytime I cancel out from the numerator, I'm left with nothing. I have to remember to replace it with 1. And in the denominator, I'm just left with cosine. And so at the end, I can just simplify this using my reciprocal identities again. This would be secant x. All right. Just a couple more examples. Find all values on an interval 0 to 2 pi that solve cosine cubed x over sine x equal to cotangent x. Okay, now we're more solving an equation. Okay, we're not simplifying, but simplifying expressions helps solve equations because it makes it a lot nicer. So let's go with cosine cubed. Oh, let me rewrite that. Cosine cubed x over sine x. And you know what I'm going to do? I'm going to take time to write cotangent in its cosine sine form. That's a quotient identity. One of my quotient identities is that cotangent is cosine over sine. Now, this is nice because what we have is two fractions with the same denominator, sine x. So I can multiply that out. To simplify it down to just being cosine cubed x equals cosine x. Now, this is where we kind of got to get a little bit back into algebra. It's tempting to want to say, oh, I'm going to divide out at cosine x, but that could remove some possible solutions. So what I'm going to instead do is I'm going to subtract cosine x from both sides. Cosine cubed and cosine are not like terms, so I'll have to write it as an expression. Cosine cubed x minus cosine x equals 0. But now look at what we have. We're going to use a technique called u substitution. If I let u, remember this is cosine cubed, so I'm multiplying cosine 3 times. If I let u equal cosine x, I can think of this as, okay, well, if this is multiplying cosine 3 times, and I set this expression up, then that could be the same as saying u cubed. And then I'd replace this cosine with just u. And now it's starting to look a little bit more like polynomials that we're more used to dealing with. So using factoring, I see I can factor out a u. So I'm left with u times u squared minus 1. And then I can use my zero product rule. U equals 0. And u squared minus 1 equals 0. All right, now let's bring back in cosine. The u substitution was just to demonstrate what we can do to factor this. It isn't a polynomial, but it behaves like a polynomial in solving the problem. So I'm going to instead now write this as cosine x equals 0. And actually, I'll do a little bit more work with this one first. I'll go ahead and add 1. I get u squared equal to 1. And then square root. And I get u is equal to plus or minus 1. And that means that cosine x is equal to plus or minus 1. Now, this is where your unit circle will come in handy. We want to search for where all the cosine values equal to 0 from this expression. and look for all the cosine values that equal plus or minus 1 on the unit circle. Now, the interval that restricted us in the very beginning is nice. It goes from 0 to 2 pi. That's what our unit circle goes to. So we don't have to think anything beyond outside what our unit circle tells us. So remember, cosine is the x coordinate on the unit circle. So where is the x coordinate 0? Well, that would be at x equals pi over 2 and at 3 pi over 2. Now, let's think of this in terms of two equations. So where does cosine x equal positive 1? Well, that would be at the location of 0 and 2 pi, but our interval indicates that we don't want to include 2 pi. Remember, parentheses in interval notations means don't include the value. So we're just going to do the 0. So x equals 0. And then we want to know where cosine x equals negative 1. So where do we have the negative 1 in the x coordinate position? That would be at pi. Okay, so to kind of round up all our solutions, x is equal to, we'll put them in order, 0, pi over 2, pi, and 3 pi over 2. And if you were to plug these back into the original equation, it would balance both sides. All right, let's go ahead, do one more equation like that. So we got 2 sine squared x plus sine x equals 1. So let's go ahead and start by subtracting 1 from both sides. There we go. Try to use a different color. I get 2 sine squared x plus sine x minus 1 equals 0. And once again, it looks like we have a polynomial, specifically a quadratic. If we let u equal sine x, then we would have 2u squared plus u minus 1 equals 0. Now, you can factor this. I believe you can factor it. Yeah, you can factor this. Or you can use quadratic formula. I'm going to go ahead and use the quadratic formula, because now that I've second guessed myself, I'm no longer sure. So b is 1, so negative 1 plus or minus the square root of 1 squared minus 4 times a is 2 and c is negative 1 all over 2 times 2. So we got negative 1 plus or minus, we got 4 in the denominator. So we got 1. This will be 4, negative 4 times negative 1 is 4 times 2 is 8. So 1 plus 8 is 9. Square root of 9 is 3. Let's go ahead and branch off. I got negative 1 plus 3. That's 2 divided by 4 is 1/2. Negative 1 minus 3 is negative 4 divided by 4 is negative 1. So now I've got my two solutions. U equals 1/2 and u equals negative 1. I shouldn't say my two solutions. I should say my two quote-unquote zeros from the quadratic formula. But remember, u is sine x. So we have to do the same thing we did in the previous problem. Let's return sine x back to the equation. Sine x equals 1/2. Sine x equals negative 1. And now we think through the unit circle. What values give a y coordinate of 1/2? Well, pi over 6 is one of them. But remember, sine is positive in both the first and second quadrant. So there's another one, and it happens to be 5 pi over 6. Okay. Now, sine x equals negative 1. Where is it negative 1 in the y coordinate on our unit circle? That would be where x is equal to pi. Okay. So find all solutions. So x, now we're going to actually write this the way we would write out our vertical asymptotes for tangent, cotangent, secant, cosecant. pi over 6 will be 1, but since we're not limited by a interval this time, I'm going to add the period, which is 2 pi n. And then we've got another one, x is equal to 5 pi over 6 plus 2 pi n. And then our last one would be x equals pi plus 2 pi n. And I'll reiterate that. The reason why we're adding the 2 pi n is because this time we're not restricted by an interval. In the previous problem, we were restricted by this interval here, 0 to 2 pi. So we only took the answers that were between 0 and 2 pi. With this one, we're not restricted by a interval anymore. Okay, so we'll add on our period of 2 pi n to reiterate every single possible solution within this. All right, last one's kind of quick. Find all solutions to the trigonometric equation cosine t equals 0.7 using a calculator where needed. Well, cosine is never 0.7 on the unit circle, so we will have to use our calculator on this one. So we're going to use the inverse cosine, 0.7. Make sure you use radians, okay? So the inverse, which is the cosine with the little -1. That's sloppy. I'm going to rewrite that. Okay. Anytime you don't get a value like 1/2 or √3/2 or √2/2 or something that's on the unit circle, you will want to resort to using your calculator. So inverse cosine of 0.7. Now, I'm not going to go ahead and calculate that. You guys can go ahead and calculate that. But remember, for whatever answer that is, again, we're not restricted by an interval here. So we're going to go ahead and add 2 pi n to that final answer. And so whatever you calculate plus 2 pi n is your final answer. Now, to reiterate, that means if you come across a question on the homework like these last three, pay attention if they restrict you on an interval. If they don't restrict you, that's when you're going to want to write it like this, plus 2 pi n, plus 2 pi n, or tangent would be plus pi n. Okay, thank you for watching. Hello, I just want to add something to the last problem in the video. I made a mistake when I assumed that this was the entire solution set. Remember that inverse cosine is restricted domain from 0 to pi. Okay, so that means from pi to 2 pi on the unit circle, we're completely uncovered. Well, cosine, especially since 0.7 is positive, remember that'll happen in quadrants 1 and 4 for cosine. So that means we've got a mirrored solution in cosine, or in quadrant 4 for this problem. So the other thing we need to do, well, we need to consider that when we're talking about the domain where we're going from 0 to pi, the other part of it would be from 0 to, or negative pi to 0, I should say. So we're talking about it being a negative solution. We're not talking about it being positive still. So negative pi to 0. That would be the domain of inverse cosine is counterclockwise to pi. The other area would be counterclockwise. Okay. So the other solution we would have is arc cosine, negative arc cosine, 0.7 plus 2 pi n. And then, again, calculate those two values, but that would be your solution set.